Okay, so please let me know if there are any audio or video problems because lately I've been having some issues with some of my other, with my regular Zoom classes. So if there is anything, let me know. Okay. Okay, so all right, welcome everybody again to the 12th session of these lectures. I had never thought that people would have the patience to sit through so many of these lectures. So I am thankful to all of you for being here. So there are a couple of things. One is that, so last time I ended with this discussion of these intertwiners, or I started talking about intertwiners. So today I will be talking more about these objects and about the other operator of quantum geometry, which is the volume operator. And then on Zulip, Takato has asked some questions, and they are really nice questions. So I wanted to just talk a little bit about those, in person. So now, for instance, one of the questions that he has asked is, what is the relationship between the Kodama state, which is a solution to the Hamiltonian constraint, and graph states? So as far as I know, nobody has come up with a sort of a spin network representation of the Kodama state. So what your question amounts to is the following: that so we can write down the Kodama state, right? And again, in some ways, it's a formal expression because of issues having to do with normalization and so on. But anyway, so we write down this this expression, right? I'll just put LCS, right? And so if you want to, so what your question basically is that, so let's say that we have a graph state, right? Which is some spin network, right? So we have a graph with some labelings, with some spins and so on. And how can you express this state as a superposition of these graph states? So in other words, what is, let's say, what is this quantity? So let me call this something else. Let me just call it gamma, the graph state gamma. Or actually, I should also mention gamma comma ji, where ji is a collection of labels. So then the question is, what is this quantity, right? Does this make sense? So again, this is a nice question, and it amounts to understanding how to write down some operators which act on these graphs, which would correspond to these terms in the Chern-Simons Lagrangian, right? So if you look at momenta, right? If you ask what is the action of these momentum operators on the graph states, that we know, right? So the momentum operator, if it acts, so not this momentum operator, but the smeared momentum operator. So I should be more careful. We have to smear the momentum operator on some surface. So I will write it like this, E of S, right? And we know that if S has an intersection with the graph, wherever it has those intersections, this gives us the action of this operator, basically just gives us the sum of the angular momenta for those edges which have an intersection. So So K is a set of points, let's say, which belong to the intersection of gamma with S. So let me write that a little bigger. Gamma intersection S, sum over JK, or if you just write it as an operator, sum over JK in JI. Again, I should write it like this because it is a collection of spins and not a single spin, right? So this derivation just gives us the angular momentum operator on a given edge. So this we know, but it's the question would be well, if I take something like this, so if I take a term of this form, a wedge dA, right? How should I write it in some similar sense? So what is this? Let me just write down. E of S is equal to the integral of d2x over some surface of EAI tau I times the normal to I. And again, putting all this to the right, this function of x. So it becomes integral of d2x NA tau I, and then minus IH bar del by del AI of x, like this, right? So this is the this is what I would this is the volume of the action of the flux operators on the graph edges. So when this derivative acts on this graph state, right, it just gives me the angular momentum operator acting on those edges which pierce the surface S. Otherwise it's zero. So this question amounts to asking, how do I construct a similar operator or similar action for these quantities, right? Now A wedge dA is a three form, right? So if I write A wedge and without any operator, this thing. So what is this? This is like epsilon ijk a mu so alpha beta gamma, alpha beta a gamma, and or these are all spatial. This is three-dimensional, so I should probably use epsilon ijk times this times epsilon abc, and there might be some factor of 1/2 or something like this, right? So this object is a three form, right? So it's something that acts on a volume, right? So for example, this flux operator was smeared on a two-dimensional surface. This is something that acts on some volume, right? So what I would do is I would define, if I want to write down an operator for this, let me call that operator, let's say something like this, chi of A, right? So I would say similar to this definition, I would say something like this: integral over some probe volume, okay, of d cubed x, right, trace of A wedge dA. And now I would ask the question that I have my graph. This is my graph, so it takes a long time to draw a graph which looks sort of random and halfway decent, so I'll just use the same graph. And then I ask the question, I have some probe volume. This is, let's say, right? This is the volume. And in this example, in this diagram, this volume intersection with gamma is not the empty set, right? So again, if the volume intersection with gamma is 0, right, you get 0. But if it's not 0, then the question is, so how do you define these operators acting on this state? And it's not immediately clear to me how to do that. Okay, and I don't think anybody has really worked it out. When I think about it now, it seems that it should not be too difficult to understand. But yeah, I mean, this is an open issue at the present moment. So if you can come up with a way to write down such an operator, let's say chi1a and chi2a, again, the other term. So you know the function, you know the form of this graph state. If you write it as a cylindrical function of holonomies, you have this gamma is equal to psi of g1 g2 till gn, right, where n is the number of edges. And then right, you would have to ask, how does this connection A act on these holonomies? So my guess is that you would do something like this. This holonomy is the path ordered exponential along any given edge of the line integral of the connection along that edge, right? And so if you have the connection, some connection operator like this, let's say a bj acting on this g. Yeah, sorry, I mentioned the cylindrical functions. I'll just talk about that in a second. Then my guess would be that this would be just like a multiplicative operator, like the position operator, and you would get like something like this, a bj times g, right? But again, in order to define this operator, you would have to smear it along a one-dimensional curve, right? The same way that we smeared this thing along a two-dimensional curve, right? To define this an operator corresponding to the connection, you would have to smear it along some one-dimensional curve. Then you would have to ask, well, how does that curve, if that curve has any intersection with the edge on which it is acting, you would get a non-zero answer. So again, there will be a lot of intricacies involved. So no, to the best of my knowledge, nobody has gone into those details. It would be nice if somebody did that. Then another question was that, can we follow the time evolution of a graph state, right? And the answer is no, because, well, as you said, the Hamiltonian vanishes, right? So how should you, what is the meaning of time evolution in the system? So the best thing that we can actually say is that if you want to ask what is time evolution or what is evolution of any kind, right? Evolution will correspond to discrete changes in the graph. Okay, and it turns out that if you look at the Hamiltonian operator and ask what is the action of this Hamiltonian operator on these spin network states, okay, this can actually be evaluated exactly, and it was first evaluated by Theban. And what it does is that if you look at a single vertex of your graph, and you imagine what is the action of this Hamiltonian on this single vertex, well, what it does is it takes this vertex and adds a loop adds a loop to that vertex. So then you can take all of the you can take the full graph and just break it up into, you can just cut it at every edge, so you get a collection of vertices, right? And then you can act on each vertex with this operator, because this operator is not causing any interaction between the vertices, right? It is just generating this extra closed loop. And so the question, well, I mean, it's not clear in what sense is this, it is giving us any kind of dynamics, right? Because for instance, if you calculate the area associated with this edge, what will happen is that, right, I look at some surface, and if I look at some surface which is intersected by this edge, what will I get, right? I will see that you have, at one point the edge is going up through the surface, at the other point the edge is going down. So the net area contributed by this edge to that surface would be 0. Okay. So because the area has a sort of a direction, right, which depends on the orientation of the edge when it pierces the surface. So these loops also have an orientation. So right, these are oriented loops, and all the edges are oriented edges. Something like that. So if you ask what is the effect on the area operator due to this Hamiltonian, you would get 0. Similarly, if you asked what is the effect on the volume operator, you would again, I think you would get 0. Yes, Mustafa.
Yep, I had a few questions. The first one is related to our current discussion, and that is the overall effect of the Hamiltonian operator on the graph state a gauge transformation?
Well, I don't know. I mean, how to think of no. The answer is no.
My second question is in our previous discussion, we spoke of how three forms will act on the graph state. I understand that part completely. I do not understand how that will give us any information about the inner product that you wrote down on the second line or the third line.
I'll have to go back to the whatever you'll have to tell me where. In the last lecture or before?
No, that? in this lecture only.
Oh, in today's lecture. Oh, sorry. Okay, yeah. Tell me.
So could you go back?
So your question is how will that give you any information on this inner product? So I mean, we write this as a functional, right? In terms of the connection. So if you look at this object, it will be this functional acting on this graph state, right?
Okay.
Right. And also I forgot to mention very importantly, this functional, there is an integral over well, no, maybe not. Okay. So this is defined for a single connection, right? This is defined for a single connection. Like this. For a single configuration of the connection one form on the three manifold. Right? So you would write these as operators. So maybe you know, rather than thinking of this as an inner product, maybe it's better to think of this as an operator psi acting on this state. But I mean, whether you think of it as an operator, you can think of states as operators, or as, I mean, there's a dual description, right? So so rather than you know, doing something like this, maybe you could put a bra and a ket of psi k or something. I mean, again, like I said, the details have to be worked out. But you can see like how one would do that, right? You can see how one would go about doing it. But there are all these issues regarding the definition of some sort of a connection operator. So you would have to define this connection operator. You would have to again smear this along some curve gamma, right? Like this, and so I'll just forget about all the other things. I'll just write this as a dx, or just integral of a. A is a one form. I can integrate the one form, and then I would ask, how does this a gamma act on the holonomy G, which is defined along some edge E. So I have some edge E, and I have this path gamma, right? So if gamma intersects E, only then I would get some non-zero expression for this operator. Otherwise, it would be zero, right? And then I would have to ask, well, what happens at the intersection, and so on and so forth. So again, it's not, I mean, obvious how one would go about doing that. Okay, at least I have. I mean, I thought about it only after Takato raised this question, and so that's why I thought it's a really good question, which deserves to be talked about. Then this Thiemann construction of this Hamiltonian operator, I will, time and interest permitting, I will show you how this comes about explicitly. You can actually show this. It's a nice derivation. I worked it out once, and I was very proud of myself for being able to work it out. So I would like to share it with you if that's possible. Then the next question that he asked is, well, what is the energy of a graph state, right? I mean, it should be possible to evaluate some sort of an energy. Yes.
Can I ask you a question?
Yes.
I'm a bit confused about the definition of Kodama state. So
okay,
you
sure.
State can be viewed as an operator, but what is the basis of Kodama state? The right-hand side seems to be an operator, and the left-hand side seems to be a vector in Hilbert space.
No, you're right. I mean, so this is, so at right now this is a state. Both sides are states. Okay, so instead of writing it like this, maybe it's better to write this like this, psi of Ka, and sorry, psi of K. And then if you want to write down the full state, you would probably do something. You would have an integral over all possible connections, like this, something like along these lines. And then you would say there is some ket A basis, right? So then if you talk about taking this inner product, then this inner product would be something like this. You integrate over all connections, psi Ka or gamma Ji psi K A, right? Something along these lines. But again, this is a, I'm just writing something down formally.
Yeah. This makes sense to me. Okay.
The right-hand side, Agda sir is saying the right-hand side is a wave function in A representation. That's right. Sorry.
Another question. Oh, sorry.
Yes.
My another question is, so any physical state must satisfy Hamiltonian constraint, right?
That's right.
And so, given some graph state, if you want to project to the physical state, then you have to impose the Hamiltonian constraint. Is it
right?
Right.
Right.
So, so any physical graph state must be Kodama state as well?
No, the Kodama state is only for when you have a non-zero cosmological constant, right?
Yeah.
That's the first thing, right?
Yeah.
Okay.
Okay. So well.
So I mean, okay, let's say that you take the cosmological constant to be non-zero. Fine. You say that the Kodama state is your state.
It's the physical state, right?
Right. And then what?
And the graph state, so graph state was introduced as a gauge invariant state. Am I
Right.
correct?
So graph states are gauge invariant, and I didn't talk much about the gauge invariant properties. So there are two different kinds of gauge invariances, right? One is under diffeomorphisms of the spatial manifold. Okay. Now graph states by construction are invariant under diffeomorphisms, spatial diffeomorphisms, because only the graph structure matters to define the state. You don't need to put any coordinates on the vertices. All right. So you have an edge, right? And if you have a diffeomorphism of your manifold, then well, the edge is changed to a different edge. Okay, whatever. I mean, something, doesn't matter what it is. But the holonomy along the edge will remain unchanged, right? So if this is G, this will also remain G, right? This is one kind of symmetry. The other thing are the gauge transformations under the SU2 gauge transformations, under the SU2 gauge transformations, what happens is, so if I have an element G, H of SU2, or I have a H is a gauge SU2 gauge transformation, which means it's a map from my, like, it's a function, it's an SU2 valued function on my spatial manifold, right? So at each point on my spatial manifold, I have a element of SU2. Then the way these gauge transformations act on the holonomies is as follows. So if I have a holonomy G, and this is the source vertex and this is the target vertex, right? So now this gauge transformation is defined on every point on my manifold, right? So in particular, I will have the value of this group element at HS and also at HT, right? Gauge transformation at the target and gauge transformation at the source of the vertex. Okay. So now what happens is that under this gauge transformation, the holonomy transforms as follows. It becomes HS G HT inverse. So this is the way the holonomy transforms. So if you consider, for instance, two different edges, okay, so this is G1 and this is G2, and there could be other edges here also, it doesn't matter, but you just consider what happens if you go from here, if you go along this edge, along this path, which is the union of these two edges, right? So if you look at the action of this transformation on these two edges, what will happen? So you will have, let's call these points, let's give them some names. Let's call this point A, B, and C. Then G1 will go to HA, G1, HB inverse. and don't want to put this on the next page. So just 1 second. Let me try and squeeze everything in. Performing a gauge transformation on my notes, a diffeomorphism to be more precise. So G1 will go to this, and G2 will go to HB, G2, HC inverse. So if I ask what happens to the holonomy along the union of these two edges, right, that is G1, or I should write it as G1, G2 or G2, G1. Again, I don't know, I'll just write it as G2, G1. What happens is that, so if you take the product of these two, the HB inverse and HB will cancel out, and you will get HA, G1, G2, HC inverse, right? Which is what you, right? Which is, so this consistency is there, right? So this is how these gauge transformations act on edges. And so if you consider, if you consider a graph which doesn't have any loose ends, right? That means there are no edges which end in a single vertex, right? So if there are no dangling edges, so to speak, so a dangling edge is like you have some graph, right? And then you have a edge which comes out of it and doesn't go anywhere, right? So how does a gauge transformation act on such a state, right? On the interior of the state, everywhere, the SU2 gauge transformations acting on all of the edges, they will all cancel out and give you identity, right? So for example, you can look at some state like this, okay? Let's say, right? So this is a I don't know what the technical term is for a graph which doesn't have any dangling edges, a truncated graph or something, a loop graph. So now if you look at the holonomies along all the edges, right, all of the gauge transformations will cancel out. But if you have a single edge out here, a dangling edge, then what will happen is here at this vertex, the gauge transformation will not vanish, right? So what happens with this dangling edge? With this dangling edge, it goes as H source G H target inverse, right? But this H source will be cancelled by the gauge transformation acting on these other edges. Okay. So for instance, if I look at this edge coming in, this edge will go as something over here times something over here times something over here inverse. So if I look at this whole path, again by that same sort of reasoning I explained here, right? These two elements, they multiply to give you the identity, right? So this whole state would be invariant as long as I didn't have this edge hanging here. But the moment I have this edge, there is a unaccounted for transformation at the end over here. So if you have an if you have these vertices, right, these open vertices. So I have some graph, I guess you could call it a hairy graph, right? Haridas sir is saying for the graph you have written gauge transformations do not cancel. Which Which graph is that, sir? Are you talking about this whole graph or only this part? So if I have a graph which doesn't have any hair, such graphs will be gauge invariant. But if I put hairs on the end, what happens is that at the end of each hair, you get a gauge transformation. Now that gauge transformation has to act on 1 second, sir. Then that gauge transformation has to act on something. It has to be absorbed by something. So one way to think of it is that these endpoints, they correspond to fermions. They correspond to, so if at the edge, if at each vertex you attach a single fermion living in the fundamental representation of the gauge group, then under the gauge transformation, what would happen is whatever is on the interior, everything will be, all the gauge transformations will go to identity. And at the vertex, the vertices would just experience the gauge transformation at these target vertices, boundary vertices, as this. Right. So this object would absorb that gauge transformation. Anyways, so the thing is that you have these two kinds of gauge transformations. And why did I start talking about gauge transformations? Because Takato asked a question and I forget what the question. Right. So yeah. So these states are invariant under spatial diffeomorphism by construction. And if I look at these graph states in this way, then they are gauge. I would say they are gauge covariant. Right. So for instance, if I have a graph state of this kind, I can associate with this state. I can write it like this: psi1 tensor psi2 tensor psi n, where these are the fermions attached to the boundary surfaces of the or the particles attached to the boundary edges of the graph. So if I ask what happens under a gauge transformation to this graph state, well, this graph state goes to another graph state where each of these particles has transformed like this. Okay. Now Dev Malya is asking, why is it not a scalar or a boson? Yeah. So I mean, right. I guess I shouldn't call it a fermion or a boson. I should just say that it is a state, a vector in the. So if you're talking about so it depends on. So when you look at the spin network decomposition, in that case, these things will become either bosons or fermions, depending on the labels of your edges. Okay. So these are the gauge transformations. Now, what was your question? I forgot about.
Well, my question is, so the natural requirement for states are gauge invariance and satisfying Hamiltonian constraint, right? And these two requirements are different.
Which two requirements again?
I mean the satisfying Hamiltonian constraint and gauge invariance. And gauge invariance is obvious when we talk about graph state. But Hamiltonian constraint is what we need for physical states, and
for physical states, right?
yeah.
So right. So like I said, we know that the action of this Hamiltonian constraint has this form, but it's not clear how to give this the interpretation of some kind of dynamics. Okay. Now, so to sort of get around that, people came up with this spin foam picture. Okay. So what is this? What is the spin foam? I'll just mention very briefly because, well, yeah, you have two different spatial slices at different times, let's say, or two different leaves of your foliation, right? And you have some graph state defined here on this surface, and some graph state defined here on this surface, right? Okay, very pretty, right? And then you ask, well, how can I go from this state to this state, right? So now it turns out that so you can ask, so you can define certain moves on the vertices of a graph. These moves are known as partner moves. Okay, so what these moves do is that they exchange. If I have, for instance, a trivalent vertex, one move can write this vertex as a superposition of. So this move is called a 1, 2, 3 move because you have one vertex and you are replacing it with three vertices. In a similar way, one can write down a 3 to 1 move. So here you have a sum over. You will have a sum over all the j labels in the interior. And then in a similar way, you can write the inverse of this. It will be something like this. So in condensed matter, this is known as a star triangle transformation, by the way. If star triangle transformation. And then you can have another move, which is a 2-2 move. I believe this is the 2-2 move. And so you can use a combination of such moves to go from any one graph to another graph. Right. So you can start from a graph and then keep performing these moves. Let's say partner move 1, partner move 2, gamma 2, partner move 3, gamma 3, and so on until you get to your final configuration. And when you look at the 4-dimensional history, what it looks like is something like this. Let's say, so you have a triangle. This is the graph. These are vertices defined on sigma on the initial surface. Let's say sigma. And then how do you go to the next surface? On the next surface, on the next time slice, so to speak, these are the edges. And then these edges are connected to your. So this is let's say sigma t, and this is let's say sigma t plus delta t. So you have and these edges have a time-like orientation. These edges which connect the spin network states, right? The two different spin network states. So what you will end up with is you will end up with a bubble kind of picture. So you will have a sum of histories. You will have many different possible ways to go from gamma to gamma prime, right? Just like you have for a single particle to go from x to x prime, there are many, there is more than one path, right? And then you write down the amplitude of the particle's propagation as the sum over all paths, right? Or the sum over the exponent of the classical action associated with each path, and then you sum over all the paths, right? This gives you the transition probability between the particle being at x and the particle being at x prime. So similarly, if you have two graph states, you would write down this transition probability, right, as the sum over all paths which connect gamma and gamma prime. Okay, and these paths would consist of these discrete series of moves on the graph states, and then you would sum over some action, right, which is defined for each path. Okay. Now, Mustafa, you can just ask. I don't know why you raised your hand.
Yeah, sorry.
Old-fashioned in that way. Yeah.
All right. So here in this picture that you've drawn with the time-like orientation, a different path would mean different green lines. Is that correct?
That's right.
Okay.
That's right. Not, I mean, and not like different green lines which just go, I mean, because again, we are dealing with graph states, so you can trivially take any path and then make a wiggle in it and shift it this way or that way. It's not going to change. It's not going to change that edge or whatever the group element along that edge. Okay. So now what happens is that, so the question is what is this action that is defined with a quote unquote graph, with a quote unquote path, right? So what is this path is that, see, you're looking at two different geometries. One is at this final surface and one is at the initial surface, right? And a single path corresponds to a single bulk geometry, right? Such that the boundary of G, the spatial boundary at some in the past and the spatial boundary in the future are the geometries on sigma t and sigma t prime respectively. Right? So the question is, how do you define this? What should be this action, right? So this action, what people have come up with, there are different proposals. One is something called the Barrett-Crane action, another is something else. So the way you define such an action, right? Ultimately, you want this to just be the action for gravity, right? Because this is the action. This action is associated with this four-dimensional bulk geometry, right? So what should be the action for a four-dimensional bulk geometry? This S path should just be the integral of from where to where? From H to H prime, where H is the three metric on the initial slice and H prime is the 3 metric on the final slice. Right? I mean, if you choose to write it in the Lagrangian, in the 3+1 form, you can write it like this, right? dt goes from H to H prime integral d cubed x, then n root H, and then you have the ADM Lagrangian, right? And n is some shift parameter. Root H is the determinant on each of the on the slices in between. Is this fine? I mean, this is what you do if you're talking about so-called quantum geometry in the path integral approach to quantum gravity, right? This is what people are doing in all of this when they're talking about all this islands and wormholes and all this. They are evaluating amplitudes by looking at this kind of a path integral, right? So basically what they do is they define the partition function of gravity in this way, right? Integral over dg, right? Exponent minus I s g, right? Where you fix the boundary, geometry of your space-time, and you integrate over all the bulk metrics which are compatible with that boundary geometry. So Z is associated with the boundary of the manifold, right? Now, in this spin network picture, how do you fix the geometry of the boundary? You fix it by specifying the spin network state in the past and the spin network state in the future. Okay. For the time being, assuming that you can ignore whatever happens at time like infinity. Okay. So let's just assume that we have two very large. So if you have a spin network which represents one geometry. So I mean, if you have that network has trillions and trillions of vertices. So you just look at a small region. So you don't have to worry about what happens at infinity at the time-like boundary. You can just focus on a sort of a small cylindrical segment and ask how do the vertices from here go to here, right? So, and how would they go? They would go by a sequence of such moves, right? But now the question is, how do you perform this kind of a sum? How do you perform this sum over metrics, and how do you define this Einstein-Hilbert action? Okay. So what is done is that you start from something which is called BF theory. You start with an action of this kind, which looks like this, B wedge F. And again, there should be a trace of B wedge F. B is a two form, okay, and F is, so B is a Lie algebra value two form, and F is also a Lie algebra value two form. The same thing. Okay. Now, if you ask what is the equation of motion of this theory, then if you do the variation of this SBF with respect to the B field, what do you get? You just, if you set this equal to 0, you just get F is equal to 0. That's it, right? I mean, you'll just get that integral of this trace of delta B wedge f is equal to 0, which means that f has to be identically equal to 0, right? Now, if you identify this f with the as the curvature tensor of some connection which is living in your space-time, like the Ashtikar-Barbarev connection, right? Then this implies that your geometry is flat everywhere, right? So so you don't get any local degrees of freedom, right? So this just becomes a topological theory, right? So this is a topological field theory. Okay. Mustafa is thinking really hard, which means that I have to clarify something.
Yeah, I think I missed something. I thought that even in flat geometry, we have two local degrees of freedom. Am I missing something here?
I mean, no, you're not missing anything. I mean, you're sure space-time has 2 degrees of freedom everywhere, right? But here all of those 2 degrees of freedom conspire to give you a flat geometry overall. That's all, right? I mean, you're picking out one configuration out of all the possible configurations, right? You're picking out the flat configuration. You can say that there are 2 degrees of freedom everywhere at each point in space-time, right? That's like looking at, let's say, the Ising model and saying that each spin can have 2 states, up and down. But then you look at, let's say, the ground state. The ground state has all spins in the ferromagnetic case. Let's say it has all spins pointing in the same direction. So we are looking at one particular state, right? And that is the extremum of this action, right? So there are no excited states. There are no states with any local excitations. This is a topological field theory. Then what you do is you add a term to this expression which looks something like this. There is some parameter epsilon, and then you say B wedge B like that. Okay. Now what happens is, now if you do the variation with respect to B, so I have written this as BC. BC stands for Barrett-Crane. Okay. So rather than BC, I'll say SF. SF stands for spin form. And now you do the variation with respect to the B field, you get delta B, right? Wedge F minus epsilon B, right? So now this would give you the equation of motion that F is equal to epsilon B, right? So this is like a symmetry breaking. You have so this is like the unbroken state. This is the state with the unbroken symmetry. And by introducing this operator, you have generated a vacuum expectation value for the B field. So this is like what happens when you look at this thing, superconductivity. So the way you model, one way to model superconductivity is that if you write down the Hamiltonian for interacting spins, what you get is the Hamiltonian for superconductivity looks like this, right? There is a kinetic term, which is just some energy, it looks like let's say Ci dagger Ci, something like this, or phi I dagger phi I, right? This is the kinetic energy of the fermions at each side. And then what you do is you have a potential term. This potential term is called a four fermion interaction. It has some value, and then it looks like this: psi I, psi j, something like this, psi k, psi l, and yeah, and you do a and then there is some delta function term which restricts the values of I, j, and kl over which you can do the sum. So this is called a four fermion interaction, right? Similar thing happens in electroweak symmetry breaking, right? The electroweak symmetry breaking, or in the Anderson-Higgs model, you add a phi-4 term to your scalar field, right? In Anderson-Higgs, what do? You start with a scalar field, with a Lagrangian for the scalar field. Let's say it looks like this. Right? And then what you do is you add something which looks like this, right? Lambda by some 4 factorial phi 4. So when you look at the vacuum of this, when you have the phi square field, so this is phi and this is v of phi, right? When you don't have this term, you get this as your potential. It has one unique vacuum. But if you have a phi square term, what happens? You get two different vacua now, right? So symmetry is broken. And when you look at it in terms of a complex scalar field, you get this Mexican hat shape, right? So it's the same thing, same idea is here. You are introducing this expression, this B field, and it is breaking the symmetry. And then one can show explicitly that this theory is equivalent to GR. This theory is equivalent to either you can say Palatini gravity or the Einstein-Hilbert gravity. Equivalent to Palatini or Einstein gravity. Okay. Why is this used? Why do we do this? Right. So we, again, coming back to the original point, we want to be able to write down an amplitude for every 4 geometry, right? We want to be able to write down something like this exponential evaluated on 4 geometries. So what is done is you start with this kind of an action. Now, why is this kind of an action nice? Because so you can define the same way that we define our spin networks, our 3-dimensional spin networks. We define our spin forms. Now the edges are labeled by representations of SL2C rather than just SU2, right? Because you're working in 4 dimensions, right? So these edges would have to be would be labeled by some boosts, let's say. And these are the time-like components. So what you have now is you define a spin foam vertex, right? So in the spin foam vertex, right, now your edges are labeled by elements of SL2C, okay, or representations of SL2C. So now this G1, G2, G3, and G4, these are elements of SL2C. And when you do the analogous spin network decomposition, what you would get is that the corresponding spin network basis states would be labeled by representations of SL2C. Now SL2C can be written as SU2 times SU2, right? It can be written as 2 copies of SU2. The Lorentz group can be written in terms of, right, so if you want to write down the representation levels for SL2C, how do you write down the representation for the SL2C algebra? You can write it down using 2 SU2 labels. So J1 and J2, these are SU2 reps. So if you specify 2 representations, right, that is the same as specifying a single representation of SL2C. In case you have forgotten all of this, which is very, very natural for most human beings, even very smart ones, I suggest that you go to Peskin, which as always remains my favorite reference for anything related to life and physics. So you go to Peskin and you look in chapter 4 and you look in the exercises section. There's a very, very, very beautiful set of problems which ask you to show this. Okay. What you do is you look at the Lie algebra of SL2C. The Lie algebra of SL2C so the SL2C consists of boosts and rotations, right? The Lorentz group consists of boosts and rotations. So you have L, which are the rotations, and you have K, which are the boosts. You have 3 boosts and 3 rotations, right? And then you can construct L plus minus IK. You can call this J plus minus, right? And from the commutation relations of the SL2C generators, you can show that J plus and J minus, these individually satisfy the SU2 commutation relations. So if I look at J plus I, J plus J, I get epsilon ijk J plus K. And same thing for J minus, so I can put plus minus. Right? So now for my 4-dimensional spin networks, what I would do is I would label each edge with 2 copies of SU2. So JA1, JAB. AB refers to the copies, 1 refers to the edge. Then this would be JA2, JB2, and so on. Okay. Now, yeah, sure, Dimolya. SL2C is the double cover of the Lorentz group. That's fine. We have no issues with that. Okay. So right, and that just means that if you look at when you say double cover, right? What does that mean? That means for a single element of SL2C corresponds to 2 possible elements of SO31, right? But the Lie algebra of SL2C and SO31 is the same, right? Just the same way that the Lie algebra of SU2 and SO3 is the same. And SU2 is the double cover of SO3. Okay. Now, this corresponds, one can show that you write down the vertex. There is a vertex which corresponds to these spins. There is a certain way of gluing together all the spins that come into the edges, right? And that vertex, one vertex is called the Barrett-Crane vertex, for example. And one can show that that Barrett-Crane vertex is the discretization of this action, this BF action. Okay, so if you take this BF action and you discretize it, right? And and then you label all the edges with SL2C elements, you will get this picture. Okay. Now, what happens is that we don't want the BF model. We want GR. We want general relativity. So how do we get general relativity? We get general relativity by introducing this term. This term implies this constraint on the 4-dimensional curvature. F is equal to epsilon B. It turns out that this constraint is equivalent to saying that your spin labels are the same. JA is equal to JB. And so this is called the simplicity constraint. So if you construct your 4-dimensional spin networks with your edges labeled by 2 copies of these J's, right? And then I haven't mentioned what the vertex looks like. That is very important, but I haven't mentioned it. But I haven't mentioned the vertex in the 3-dimensional case also. Actually, today I was going to talk about that. I was going to talk about the volume operator, but then I've been completely sidetracked and talked about other things. So when you look at these 4-dimensional spin networks with the simplicity constraint imposed, these are the quantum states of geometry corresponding to Einstein gravity. So to come back to the original question, how do I write down the time evolution of states in loop quantum gravity? I specify my spin network state. I specify my initial and final spin network states. Then I say that there is some spin foam configuration. So this spin foam now is a spin network in which has labels, edges labeled by these JJ representations, right? But it's also basically a big graph. It's a graph. It's a graph whose boundaries are this graph and this graph respectively. And then I sum over all the possible spin form configurations which connect sigma t and sigma t prime. And that gives me the amplitude for transition between one metric and another metric. And that is the quantum gravitational, the sense in which that is the quantum gravity transition amplitude.
Well, I have a question.
Yes.
Well, in case of let's see, ordinary quantum mechanics or quantum field theory, the partition function is given by vacuum to vacuum amplitude, transition amplitude, and so you can act exponential IHT on the vacuum and take a limit of t goes to infinity and
right.
act
Well,
of vacuum. But here,
you give t a small complex. You make t complex, I think, and then you take the limit. Anyways, yeah. So then you get the vacuum state, right? That's what you're saying.
Yeah.
Right. So in terms of if you work with the Euclidean picture, then what you're saying is that right, minus tau h acting on any state, limit tau goes to infinity, is equal to the vacuum state, right? This is the statement, I think. Am I right?
Yeah. And but here, so the Hamiltonian induces a loop for each body.
Right.
And doesn't change the structure graph.
Right. So now that's what I'm saying is that this is one candidate for H. Okay, this is one way of looking at the action of H. And I mean, if you follow all the rules properly, this is the result that you get. Okay. But I have my own ideas about how to implement this Hamiltonian in a way that you get a non-trivial action on spin networks. But I haven't written any paper about it. I have the idea, but I don't know. The thing about me is that I live, I mean, like all of this loop quantum gravity stuff might seem very mathematical to many of you, but trust me when I say that the real loop quantum gravity people, they just look at all of this as they eat all this mathematics for breakfast, right? So with respect to the hardcore loop quantum gravity people, I am very much in the hand waving sector, right? My understanding of the mathematics involved is very, very basic compared to what all the other people do. Okay, so that is my handicap. So when it comes to making my ideas concrete, I suffer because of that handicap, unfortunately.
Deepak, I have two questions.
Yes.
The first one is, could you go back to the last line that you wrote, where it was you wrote down an expression in Euclidean time? Yes, I do not understand why the right-hand side has to be 0 if the Hamiltonian acts on the
No,
state.
not 0. This is the vacuum state.
Yep, I don't understand why the right-hand side is a vacuum state, because if the Hamiltonian acts on the state, that will give me a 0, and that should just give me psi back,
No,
right?
no. No. So what this is the usual quantum field expression. This is not when the Hamiltonian is 0.
Is a constraint. Okay. My second question is, so our previous discussion was how do we write down the amplitude in going from one graph state to the next? Could we reformulate this in without using the canonical picture at all?
Yeah, that's what we do, right? That's what this whole BF thing is about, right? So this is all completely covariant, right? And so the spin form language is covariant loop quantum gravity, and the spin network picture is canonical loop quantum gravity. Now, after this idea of spin form was invented, for a long time there was a lot of debate whether spin forms and correspond to spin networks. That means if I do look at the boundary of a spin form, do I get exactly the canonical theory or not? Right? And then that has been shown to be indeed the case. So covariant loop quantum gravity and canonical loop quantum gravity, they match up precisely. And very quickly, I'll mention, since I have a captive audience. Okay. So Haridas sir is mentioning something important, that for the large Euclidean time you get vacuum state depends on the Hamiltonian being bounded from below. So bounded from below means that it has a minimum lowest eigenvalue, which is the case for anything that we consider physical, right? Unless you are thinking about something like an inverted harmonic oscillator or something like that. But then those are unstable systems. So while I have you all sitting captive, let me quickly mention my idea for this modified Hamiltonian constraint. And it is as follows. So when you consider the action of this Hamiltonian on a single graph, on a single vertex, you get this loop, right? Now what happens is that you have to take certain limits, and in those limits, what happens is that the loop actually shrinks down to 0. Okay, when you take all those limits. But let's say for speculation's sake that you don't take that limit, okay, and you say for some reason that loop remains of a finite size. Maybe, I don't know, some sort of quantum fluctuation or whatever, something, right? And then you look at the action of this Hamiltonian on two different vertices. Okay, now these two vertices could be far apart or close to each other in the graph. I mean, we don't know. There are some two vertices, right? Well, what happens on each vertex? On each vertex, you get a loop excitation like this. Okay. Now let's say that you don't take this limit in which these loops shrink to 0. Okay. Then what is possible is the following. What is possible is this. These loops could intersect with each other. right? Like this. Okay. So this is still acting on right, something like this. And then what one can do is one can use certain decompositions. So you have an overlap here and you have an overlap here. So you can look at this overlap of these two edges, which looks like this, let's say. And then one can show that this can be written as something which looks like this plus something which looks like this, with the appropriate orientations on all the arrows. Right? In terms of knot theory, these are known as Skine relations. And these are I mean, you can define them when you talk about the connection on a graph. And remember, we are talking about connections on graphs, right? So if you have a state like this, it can be decomposed as a linear superposition of two states, which one state which looks like this, one state which looks like this. So this thing can be written as a superposition of wait, what did I just do? No. This thing can be written as a superposition of the state without any linking. Okay. Like this, which would correspond to this configuration, but also the state which has a link which goes like this, a pair of links which go like this, which corresponds to the second possibility. So now what you have is that the Hamiltonian operator is producing linking between pairs of vertices, this modified Hamiltonian operator. So anyways, there are many technicalities and subtleties which I have not worked out, but this is just something to maybe chew on if you want to chew on something.
Deepak,
yeah,
I think you need a closed loop for the second one. You just omitted.
For which one?
The second term. For the second
This
term,
term?
you have one closed loop, right?
Oh yes. No, you're right. I'm only looking at one vertex. If you have to look at the second vertex also. Mm-hmm. Sorry. So you have to look at this. This is just one, and then you have to look at the second one also. So what you would get is you would get one of these, and then the other one like this. So you would get this plus this. This would again be something this plus this. And like I said, I've to look into it in detail and see if it actually gives me anything non-trivial. But if it did give me something like this, then you would have some non-trivial action of the Hamiltonian on your graph states, right? Anyways, I will stop here for today, and I think we have covered a fair amount of material today, which is we talked about, let's say, the spin network representation of the Kodama state, or the possibility to write down such a representation, or and the second thing, we start talking about the Hamiltonian constraint and time evolution, which leads us to the picture of spin forms. And canonical and covariant quantum gravity, covariant LQG, plus some speculations. Okay. Actually, so I had hoped to talk about the volume operator and intertwiners for three-dimensional spin networks, but we ended up talking about something entirely different. That's fine. So, so today was the 12th session. Now there are several more things which is remain to be talked about before we can, I mean, again, if there is interest, which is the remaining topics that I would like to cover are the following. I would like to talk about loop quantum cosmology. Then I would like to talk about coherent states, which are one possible route to defining a notion of a semi-classical geometry. And then, of course, this tensor network connection. Tensor networks and tensor networks, spin networks. And then, well, if there is an appetite for it, my own work on quantum error correction in LQG and holography. So my expectation would be that this would take another at least 2 sessions. So can I once again get a head count of anybody interested in these topics? And if you have had enough of LQG, that's, you know, you can, you know. Okay. Well, Deva, you don't have an option in this matter. Deva is my student, right? So she better come to it. Anything, no matter, even if I'm just like singing limericks or something, she has to show up. Okay, so all right, then we'll meet again on Friday for the next session. And again, whether any of this will lead you, any of you, to conducting actual research in loop quantum gravity or not, maybe, maybe not. But at the very least, my hope is to leave you better equipped to understand what is going on in the loop quantum gravity community, and to be able to, better understand as an entry into research, right? If you do choose to do research in LQG, you will have to invest substantial more amounts of time to actually learn all the basics. So if you are interested, I strongly recommend there is a book by Rovelli and Vidotto called Covariant LQG or Covariant LQG. And it's a very beautifully written book. You might have to supplement this with other references. Probably, you probably would. But yeah, I would recommend this. And yeah. Okay. So yeah, I mean, just for as example, like attending a 12 or 14 hour set of lecture courses on string theory would probably not leave you equipped to do research in string theory. It would just give you a basic, you would just learn an outline. Because we are talking about 30 years of research work that has been done, right? And in string theory, we're talking about 50 years. So Deb Malya is asking about a short review. Well, if you're looking for something short, then you can look at my little book on LQG. LQG for the bewildered. Okay, and this is short. This is 1/4 the size of the Rovelli Vidotto book. And again, we have tried to cover all the major topics, but then again, this doesn't really cover any of the more important developments that have happened over the past 10 years or 15 years. So, and this is a very active field of research. So yeah. And some of the things that people are doing, some of the very interesting things people are doing now is, for instance, people are using quantum computers to evaluate these spin network transition amplitudes. And much of this work is being done by people in by Chinese researchers. So this is actually being done on hardware, not theoretically, right? They are setting up these quantum states which correspond to, but of course these are not states of quantum geometry, right? I mean, of quantum gravity. These are just right. You are just running the simulation on a quantum computer. But it's still very, very nice to see that work. And yeah, I'll stop there. Okay.